Sumaya, you can start sharing your screen.
Okay.
My suggestion is that tomorrow's sleep late, like sleep till late morning. Just make sure you have enough sleep. Because if you've got good sleep, then you'll be able to recall well.
Yeah. Should I start?
Yeah.
Okay, merge sort is one of the most efficient sorting algorithms. It's based on a divide and conquer strategy.
Hmm.
So merge sort continuously cuts down a list into multiple sublists. It breaks the list into half and continues until each sublist has only one item, and then merges those sublists into a sorted list.
Okay.
So the algorithm is check if the left index of the array is less than the right index. If yes, then calculate its midpoint. So this check is just to check if the array has more than one element.
Hmm.
And then calculate its midpoint. Then divide the array into two halves using its midpoint. Further divide these two arrays into further halves until the atomic units of the array is reached and further division is not possible. Start merging the elements again based on comparison of size of elements. Compare the
I think
element for
I think it'll be more clear if you just show us visually also how
yeah.
things are
I'll
done.
show the example on the next slide.
Okay.
Yes. So the last step is to merge by comparing the elements for each sublist and then combining them into another list in a sorted manner.
Okay.
So this is an example. So the merge sort algorithm is like this. Left is the leftmost index of the array, and right is the rightmost index. So if left is less than right, this is to make sure that the array has more than one element. Then we get mid, and then perform merge sort on the left half from left to mid, and merge sort on the right half from mid plus 1 to right. So these steps would divide the array into two halves, and then those would further be divided into halves until they cannot be divided any further. So right up to here, this is the dividing part, and then next we have to merge the sub arrays.
Okay.
So
I'm just trying to
so
understand the first step first. So if left is less than right, what left are we talking about? What part of the elements are we talking about? Start from the beginning.
that's index.
Index of
Leftmost index and rightmost index of the array
which
to
is
be
6 and
sorted.
1.
No, the index. So in this case, it will be 0 and uh, 1, 2, 3, 4, 5, 0 and 5.
So if 0 is less than 5, then we will calculate a mid, right?
Yes.
But that'll always be the case, wouldn't it? It'll always start with 0.
It won't always start with 0 because we'll be dealing with subarrays also. And
Oh.
the indexes of the subarrays will, like they point to the original array. They'll give the
Hmm.
index in the original array. Like this
Okay,
would
so
be uh, 4, 3 to 5.
okay, I understand. So let's start from point number 2. So initially, left is less than right because left index. They should have put the index also there. I don't know why they didn't put the index. So 0 is less than 5. So it will continue. Then it's going to find the mid, which is 0 plus 5 divided by 2. So that comes equal to, oh, there are 6 of them actually, right? So left plus
Yes.
right becomes 0 plus 5 is 5 actually. So how will that be divided?
You just take the floor of it, round it down, I think,
Okay.
if it's not an even number.
So let's say that it's 3 and 3. So 3, we got 3 and 3. And then merge sort A left mid. What's happening there? A left mid.
This is a recursive call again to merge sort, and we're giving the left half from left to mid.
So we're giving
So
A, which is the array itself. Then we're getting the giving the left. So left will contain the left index
yes, and the midpoint.
and the midpoint. So oh my god, it's confusing. The midpoint
Uh, s-
becomes
so here we're just basically giving the left half and the right half, recursively calling merge sort on the left half
no, I'm
and on
talking
the
about the
right
point
half of
number
the array.
4. Point number 4. I'm at the point number 4.
Okay.
So what's the mid here?
Mid is the middle element,
So
the
which is the
element
middle
at
element?
which you're doing the division. So
Which is the middle element?
here it will be 2. The element will be 12. The index is 2.
0, 1, 2. Okay, 3, 4, 5. So mid element
So
is 2.
we're doing merge sort on uh, A left to mid. So that's 6, 5, 12. And from mid plus 1 to right. So that's 10, 9, and 1.
Okay.
Then these functions will again recursively call merge sort. So the array will repeatedly be divided into halves until it cannot be divided anymore.
Mm-hmm.
And then we're going to start merging.
And
So
what's
we
the
call
logic of merging?
the merge function. So this is the merge function. You check if you have reached the end of any of the arrays. So we have the two sub arrays that we need to merge. If not, then compare current elements of both arrays. Copy smaller element into sorted array. So in the merge function, we have a separate array in which we are going to place the sorted elements.
Mm-hmm.
Then after copying the element into the sorted array, we move the pointer of element containing smaller element. And then if we've reached the end of any of the arrays, then copy all remaining elements of the non-empty array. So we can look at how it works using this example. So uh, when we have just these two small subarrays with only one element, it's very simple. You just compare them and put them in order. Compare 9 and 1. So 1 is smaller, it goes first, and then put the remaining element. Same with 5 and 12. 5 is smaller, so you put it into the sorted array first, and then the remaining element is 12. So we put that next. And then let's look at merging 6 with 5, 12. So first we compare 6 and 5. 5 is smaller, so it goes in the sorted array. Uh, and then we're done with 5, so we move on to 12. So we compare 6 and 12. 6 is smaller, so it goes in the sorted array. And then
Mhm.
we put the remaining element 12.
Okay.
Same with this. And then for the last one, we compare 5 and 1. 1 is smaller, so it goes in the sorted array first. Uh, then we're done with 1, so we'll compare 5 and 9. 5 is smaller. Then we'll compare 6 and 9. 6 is smaller. Then we'll compare uh, 12, 12 and 9. 9 is smaller. Then we're done with this array. We'll just add the. Oh, wait, sorry, we're not done with this array. We're done with this one, right?
Yeah. You can
Okay,
finally
so
put
you
the 12.
just, yeah, you just put the last 12. And
Okay.
here you have the sorted array.
I don't completely understand, but it's okay. I think we shouldn't be spending too much time on this one. We can move on to the next
Yeah,
algorithm.
the basic is just dividing into halves and then uh, merging them in a sorted manner.
Okay.
So the complexity of this is O of n log n.
Okay.
Maya had shared a video. It's a 3-minute video on merge sort, and
Can
it
you link
explains.
that here?
I will add that
Sumaya?
here. Yeah.
Yeah. Add it to the heading. Make the heading a link of that video.
Okay.
Hmm.
Okay.
Okay, let's go next.
Okay, so heap sort works by visualizing the elements of the array as a special kind of complete binary tree called a heap. A complete binary tree is a binary tree in which all the uh, levels are filled from left to right. So all levels should be filled except for perhaps the last level, and those should be filled from the left to the right. A complete binary tree is said to satisfy the heap condition if the key of each node is greater than or equal to the key in its children. Thus, the root node will have the largest key value. So the child nodes should be lesser than the parent nodes. So like this, we have 12, then it has children 10 and 9, which are lesser. Then 10 has children 5 and 6, which are lesser than it, and 9 has a child 1. So the root element will be the largest. Heaps are represented as arrays by first numbering the nodes starting from the root from left to right. So 12, 10, 9, 5, 6, 1. So this is the algorithm for heap sort. Build a heap with the items in the order presented. So build a heap with the unordered array
Mhm.
and modify that heap to satisfy the heap condition. Build max heap. So you modify it so that the largest element goes to the top.
Okay.
Swap, remove the root element. So the root element is going to be the largest element and put it at the end of the array. Put the last item of the heap at the vacant place. So this will be clearer in the example. Then reduce the size of the heap by 1 and heapify the root element again so that we have the highest element at root. So again, we have to modify the heap so that it satisfies the heap condition
Mhm.
that the parent node should be larger than its child nodes. The process is repeated until all the items of the list are sorted.
Okay.
So we have this unsorted array. We put it in a heap in the same order that they're given. So 285,391. Then
How
we
is it
build
that
the
you're
max.
placing them? Can you hear me?
Yeah.
How is it that we are placing it? So the order we have received is 285,391. So we are putting 2 first, then we are putting 8, then whichever is smaller, putting on the left hand side. What's the order? Like how do
No,
we?
the same order that this array is in. We're going
Okay.
from left to right. 285,391. This is not satisfying the heap condition.
Is this what you have received? Like, did we also receive the binary tree here, or did we
Uh,
just receive that column list, number list?
we just receive the list and we create the tree.
Okay, so how did we create? We put the root first, then we put the child, and then the grandchildren, and then we start from child again, and not from the child node. Like, why did we put 1 and 5 there? Why not five? Reverse of that. You
You're
see the
going in
five.
the order. We're going in the same order of the given array. So we put 2
I,
first
I
and
understand.
then go left to right, then 8, then
Okay.
5.
Yeah, but then I'm talking about the right subtree. So left subtree, I
Okay.
understand. Started from the root and went up until 9. But I don't understand the right subtree. Why did we start from the bottom and not from the top?
Where would we put it at the top?
So like replace the 5 with 1 and 1 with 5. Just switch their positions. Why don't we go with that
Mm,
approach? We're starting from top to bottom.
but 5 is already at that position. Uh,
Oh, I get it. I get it.
when
Oh, okay. Okay. Okay, I get it. So what's happening is you put the 2 and then you put these two children, which is 8 and 5. Then you start
Yes,
with 3 and 9, which and you put that to the uh, 8, and then whatever the left is, you put that there. So we have to have maximum 2 children at a time. That's the rule we are following, and we're going left subtree and
yes,
right subtree. Got it?
yes.
Okay.
So first we build the max heap. That means rearranging this so that it satisfies the heap condition.
How?
So like 9 here, it violates the heap condition. So we swap it with 8, and then it's still violating the heap condition. So it's swapped with 2. So
Sorry,
9 moves to the
can you
top.
say once again?
9 is violating the heap condition. So it's swapped with 8, and then it's swapped with 2. And then all the
What is
heap
the heap
conditions are
condition?
met.
Can you repeat the heap condition which it's violating?
Um, all the child nodes should be lesser than their parent node.
Okay, got it. Got it.
So 9 moves to the top after uh,
The two
building the
switches.
max heap. Yes.
Yeah.
So we've got our largest element. So we put that at the end of the array
Hmm.
here, and we remove that 1 from the end of the array and put it in place of 9. So we're swapping the 2.
Mm-hmm.
So now 1 is at the top, and now the heap condition is not met again. So we have to fix that. So we heapify, then 8 moves to the top.
Okay, let's wait here. So I understood till the second picture where we kind of it's not meeting the heap condition, which is the child should be smaller than the parent. So we kind of swapped the positions of 8 and 9 and 8 and 2, and finally got 9, 8 and 2. That I understood. But then, what happened in the list? How did that 9 reach there and 1 reach there?
We swap the 2. We put 9 at the end, and the end element we put in the beginning.
Hmm. Like, did we reconstruct the list? Because list was initially in an order of 2, 8, 5, 3, 9, 1. So how did the
Yes,
list
we
change?
modified the list.
So what's the rule of modification of the list? Is it like a reverse of constructing a tree? Like how we placed the numbers from the list to the tree. Similarly, from tree to the list. Is that what we did?
And no, we're only changing uh, these two.
No,
So
but see,
we
see the
just took.
initial list. See the initial list. The 9 is at the second position. Sorry, second last position. But here, the 9 is at the end. So how did it reach there?
Uh,
You see that?
yes. So
That's confusing. I don't know what's happening there.
yeah, you put the root element at the last position,
Mm.
and whatever was at the last position, you swap it and put that at the root.
I still don't understand how 9 went from second last to last position.
Oh, here I think I should have shown the array as well because it would get changed.
Yeah,
It
please.
would be 985 3 2 1.
Yeah, please do that. That's the thing. That's what I'm saying.
Yeah,
I don't know how from first to third picture it suddenly got changed.
yeah.
In the second picture, basically we followed the heap rule. So so 8 and 5 is fine because all of its children are smaller. Now 9 and 5 are not fine because the no, that is also fine. So what did we do?
Create that list for me, or maybe on an Excel, and show me what happens in the uh, second picture to that list.
Okay.
Yeah, because until it's not clear, there's no point going ahead because it's not making sense.
Oh, why is it not going back?
Oh, why did we switch 9 and 1?
Which? What?
Okay.
Oh, oh,
9 and
1.
1.
Yes.
Um, we have to put the root element of the heap at the end and switch that with the end element.
Oh,
Okay,
after
I'll
the
try
first.
to write the array here.
Yeah, yeah, right. It'll be faster, I think, if you created either table or maybe yeah, table will be helpful, or just write the number. That's fine. It's understood.
Yeah. So it's 985 3.
3, 2, and then 1.
Yes.
Yep, got it. Now I understand. It's loading. So Maya, we can't see your screen.
Now can you
Now we
see?
can. Yeah, yeah. Now it's
Okay.
clear. So now explain the third slide, third picture.
Okay. So now we had 9 at the top.
Hmm.
And it also went to the front of the array.
Hmm.
So that's the largest element, and we move it to the end and swap it
Hmm.
with the end element.
So
So
we're just
one
swapping the
goes to
first
the
and the
front.
last, nothing else. That's all that's happening in
Yes,
the third picture. Okay, move on.
yes. Then this doesn't satisfy the heap condition. So you
Follow the
have
second
to,
step.
yeah,
Follow the same
8
step that we did
moves,
in the second point.
yeah, 8 moves to the top. Then We put 8 at the end of the array, and it's swapped with 5. I
Wait,
skipped
wait,
the
wait, wait,
steps
wait.
here.
Let me digest the fourth picture here. So 8 became at the top, and 9 became. Where did the 9 go in the
We
picture?
removed 9. We removed 9 from the heap.
Why?
Because we're done with 9, that part is sorted.
Ah, okay, okay. That's why we removed it. Okay, got it. So then we left with 83512. What happens next?
Uh, so 8 is the largest, so now we push that to the end,
Hmm.
and I guess we would swap it with 2. 2
2.
would go
Yes.
to the front first, and then we
Yeah.
had to fix that so that 5 would be at the top. Then
Okay.
we remove 5, put it at the end, and swap it with the with the element at the end again.
Basically, we have to repeat the steps 1 to 4.
Yes.
Fine. No need to explain the rest of it. That's fine. But add the picture if possible later on.
Yeah.
So
I'll add the
complex. Yeah.
video also.
Why they have to
Yeah.
make it so complex? Why can't they have? Shit, yeah.
I didn't put the pseudocode for this because it was difficult.
No, pseudocode is fine, but as long as we understand the algorithm, we can write it in the exam. But yeah, this was
Yeah.
very, very complicated, and the missing of of that, that second picture kind kind of worsened the thing of understanding. So you know what? There's somebody who comes to that live broadcast, watches, and then goes. I can see there is one person watching it already. So some people just come and see like what's happening. हमको होता है ना घर में घूमते रहते हैं जाके रूम रूम में झांकते हैं क्या हो रहा है क्या चल रहा है some new story going on. So I think that's what that person does. कुछ interesting है तो
Okay.
देखते हैं otherwise we'll move on. Anyways, so yeah, thanks Sumaya. Thanks for the effort. Kritika, over to you. Let's start before we go dead. I already started to feel sleepy.
Hmm. I'll start with a nice one. So,
Okay,
and,
good.
and then
Thank
go
you.
on to the not nice one.
Okay, good. Then we can. You want to put all of us to back to sleep, like completely to sleep, huh? With the last one.
No, no, I hope not. I hope not.
Okay.
Okay. So this is insertion sort. I will start with insertion sort.
Okay.
Okay. Now insertion sort is I think it's the easiest of everything because it's
Hmm.
almost like if I give you five cards and they are numbered like
Hmm.
let's say 1, 2, 3, 4, 5, and I shuffle them and give it to you, and then I
Hmm.
tell you to arrange it.
Hmm.
So you'll pick up the first one. So let's say these are the numbers that I give you: 4, 4, 1, 3, 2, 5. Okay,
Hmm.
in this order. So you'll start with you'll put a 4 here, and then you'll check, and then the next one you have is 1. So you'll check
Hmm.
1 is smaller than will it go to the left or to the right? So you see this is
Hmm.
smaller, so this will go to the left. Then
Hmm.
you see that 3. Then the next number you have is 3. So
Hmm.
where will 3 go? Now you'll check it's greater than this but smaller than this, so it'll go in the middle. So it goes here.
Okay. Are you shifting the position of the element each time?
Yes.
The rest of
In,
the elements.
yes. So to make space for the one that we have here. So since 3 is in between these two, we shift 4 to this side and put 3 over here.
Hmm.
And then you
Okay.
have 2, and so this now. Okay.
No, no, no. Okay, let's read that. Let me read that part. This is naturally occurring sorting method exemplified by a card player. देखो ना फिर कोई आया और फिर भाग गया. So there were two people. Then again there were two people. Okay, this is naturally occurring sorting method exemplified by a card player arranging the cards dealt to him. He picks the card as they are dealt and inserts them into required position. Thus, at every step, we insert item into its proper place in an already ordered list. Okay. Why it's saying an already ordered list is because. uh, when we are placing the elements, we are of course placing it in a way that they are currently sorted. Like at point two, like point number two, it's already sorted. At point number three, it's already sorted. That's why it's calling it already ordered list. To
Yes.
find the correct position, search the list till the item just oops. To find the correct position, search the list till the item just greater than the target is found. So how it's done is that how to ensure you find the position where it's supposed to be placed is you iterate through that list and find an item which is uh, just greater than the element that you're trying to insert. So let's say you're trying to insert 3. You iterate through the list, you will find that uh, 4 is greater than 3. So that means you found the position where you want to insert, which is the position of 4, which is the index 2, sorry, index 1. So you insert that, and I guess you shift 4 to the next location. Insert the target in the vacated log. Repeat this process for all the elements in the list. This list is sorted. Yeah, that's pretty good. Thank you.
Yes. This is the algorithm, but so the algorithm for insertion sort is not given in the book, but I think Sumaya, do you want to explain it? I don't understand code at all. I'm not gonna write this if this comes.
Let me try it. So
Okay.
insertion sort. So this is what? This is a algorithm, you mean?
Yes, for insertion sort.
Okay, insertion sort array. Mark the first element as sorted. Okay. For each unsorted element x, extract the element x. Okay. For j, last sorted index down to, okay, that's what the Maya was talking about. Down to is in, I think it's an algorithm language. To rather than saying iterate from this to this, you say down to. In case if you're going in a reverse order, right?
Yeah.
Okay. So from last sorted index, you have to traverse to the uh, zeroth element. Okay. Then if the current element j is greater than, so we are treating the current element, I guess, uh, as j. Is that the current element? Possibly, or no?
Maybe
No,
the
no, no, no,
element
no.
at index j.
Yeah, I think it's the next index. X is our element. So it's saying you have to. So remember, we found we the logic is that we have to find an element which is just greater than the one we are trying to insert. So that is why here J is the element whose position we are trying to find to insert our element. So that's why we are checking if J is greater than our element. Then we that means we have found the position where we want to insert. Move the sorted element to the right by 1. Okay. Yeah, we had to do that because if you don't push the element on the right, you won't be able to actually insert your element. Okay. So to the right by 1, break the loop and insert x here. Okay. So one question. So what happens to the rest of the guys? Like, go back to that example, Kritika. So let's say, for example, at point number 4, what were you trying to insert? You're trying to insert. Okay, fine. Wait. Yeah, I'm talking about a scenario. Let's say uh, we wanted to insert something after 3, and there were already elements 4 and 5, on the right. So he, that is saying that move the fourth element towards the right. But what happens to the 5? Are we not supposed to shift that also to the right? Do we not have to shift all the elements on the right hand side to one step higher? It's not clear here.
Yes, I think so.
Oh,
Hmm.
so it means something like if you had one here and then you had five, you
Let's say
need
if you had 0 on the second position, what will happen?
zero. So four zero,
No, no. Current situation is point number 2. I give you 0 to insert. What will you do?
zero to insert. Oh, so you'll have to shift both of these, right?
Both, right? That's what I'm saying.
Mm.
As per what they are saying, just only shift the element's position which is greater than the number, which is number one, because number one is greater. So shift that to the next position. What happens to the number four? Do we not have to shift that? What happened to the rest of the
There is
numbers?
a loop, right?
Yeah,
So it will get all of the elements that are greater and shift all of them. I
that's a
think so.
little bit. That should happen ideally, but what I'm worried about is the break over there. There's a break there. Go back to that algorithm. You see that break loop and insert X here? Maybe it'll not break. Anyways, let's not break our head into this. So the idea is, I mean, it's hard to remember this entire algorithm. The idea we have to remember is uh, that we mark the first element as sorted. That's the initial thing we need to do. Okay, we have to put the first element, mark that as sorted. Next, we need to loop. Okay, for each unsorted element, let's say X is what we want to insert. uh, we have to start looping through and reach up until an element's position whose value is just greater than the one we are trying to insert. The moment we encounter that, we go ahead and start shifting that element and I guess the elements after that to one position next. So this will create room to insert our own element. So that's when we go ahead and insert our own element there, and this process will continue. And the loop is running from the last sorted index to zero. Okay, fine. Let's move on.
Or maybe they do not consider for the case that you were talking about. Maybe they do not consider that this is fixed. Maybe you can add zero here without shifting these.
Hmm, possibly. Okay, no worries.
Okay.
Let's move on.
Yes. Let's move on. Okay.
Like I
So
said, the idea of this session is not to get too much into it, but just get enough idea so that if we get something in exam, we can write something about it. Doesn't have to
yes.
be perfect.
Yes. Okay. The next one is quicksort. It is a little complicated. I'll start reading. This is exactly from the written part is exactly from the book.
Hmm.
So this is the most widely used internal sorting algorithm.
I'll
In
just
it,
use that statement, and that's it. And I'll move on to the next question. It's the most widely used internal. So I will write the same for all the sorting one.
it's
I'm sure
actually
they'll give only one. If they give one, I'll write the statement and I'll just put all the jargon and move on. Anyways, carry on. Sorry.
yes. Even I do that. Like for questions that I don't know, I write so much. Even for those, I have no idea what I'm talking about.
You write so much that you don't get enough time for the ones you know, right?
No, I finish the ones I know first.
Yeah, same thing, same here.
So
Okay, because that boosts your confidence.
yes.
Carry on, please.
So in its basic form, it was invented by C.H. Orr in 1960. Its
Okay.
popularity lies in the ease of implementation, moderate use of resources, and acceptable behavior of a variety of sorting cases. Um, and the basis of quicksort is the divide and conquer strategy. It was the same strategy for mod sort also,
Hmm.
and that is divide the problem into sub problems until solved sub problems.
Okay.
So,
Okay.
uh, and the time complexity is O n log n. So,
Yeah, so I think for both the algorithm, which is quick sort and merge sort, we can at least write 2 points which are similar, which is it's most widely used. Internal sorting. No, this is internal. That is externals. At least we know that. And then we already have jotted few points from the differences between the two, so we can utilize that. And then for both of them, we can say that they are both on divide and conquer rule strategy, which is breaking down the problem into sub problems and then
yeah,
solving each one of them. It's just like when you make target in life, and if you want to achieve a big goal in life, you break it into smaller goals, and then first achieve them, and then eventually, if you achieve your smaller goals, you will achieve the big one. Same thing here, right?
Yes.
Cool.
Okay, so this is a very basic overview. We'll get into the details in the next slides.
Okay.
So consider this one. Over here, in quicksort, one thing that we have is something called pivot. Now, pivot is by convention, we choose the last one in the term. We can also choose the first one, we can choose the random one, we can choose a medium. In the book, it says choose one. So I'm guessing they mean random, but by convention, we usually pick up the last one. So over
Hmm.
here, we choose 70 as the pivot.
Okay.
Everything huh?
Yeah, nothing, go on.
Yes. And now everything that is smaller than 70, left side, everything greater than 70 on the right side.
Hmm.
And then you continue to make the subtree. So pick up the 51, put it on the left side, right side. And then 40, 10 and 30 is smaller, nothing is smaller than 40. So this is blank.
It's not
And then
bad. Easier, I would say.
it's bad.
Than different.
Let's go,
Really?
let's proceed. It's bad.
Okay.
Okay.
The worst case complexity is of n squared, and the best
Square.
case is of n log n. So we
Okay.
had O of n squared in that earlier slide on the differences.
Hmm. So worst case complexity is what for this one? O n square, right?
One square.
Yes, this is the best case complexity.
No, no, I'm talking about the worst case complexity of this one is n
Yeah,
square.
yeah.
Okay.
Okay. Let's come to the algorithm later after we've seen the example.
Yeah, that's
Um,
better.
okay, so we have this array 265387110. Now we
Okay.
pick a pivot
So sorry to interrupt you. It's called array, not array.
array. Okay.
Yeah.
Um, we have this array,
Mm-hmm.
and we pick up a pivot. So it's easier to pick one that's in the middle because it sort of divides into two, not exactly, but like sort of.
Yeah.
So and so use the first step is simply to pick the pivot and move it to the end of the array. That's the first step you do.
Okay,
So
means
you
swap
have,
it.
yes,
Swap.
swap
Okay.
it with 0. Yes. Then then these are the two conditions that we have to remember. Um, so now the 3 is here. Forget about 3 and only watch these elements. The first step is the item. We have to find an item from the left that is larger than the pivot. So we'll
Mm-hmm.
check each item that is larger than 3. So 2 is not larger than 3, 6 is larger than 3. So we mark 6, and then
Mm-hmm.
we pick an item from the right that is smaller than the pivot. So it should be smaller than 3. So the first item itself is smaller than 3, which is 1. So you mark these two
Mm-hmm.
and then you swap it.
Swap it. Okay.
Yes. So over here you have 1 and 6. Now you had 6 and 1. You now have 1 and 6.
Yep.
Okay. And then you repeat this process. So
Okay.
again, item from the left that is larger than the pivot. 3 is the pivot. 2 is smaller. 1 is smaller. 5 is not smaller. So you
What are we comparing with?
3, the pivot.
Okay.
So you pick up item from the left. 2 is smaller. 1 is smaller. 5 is not smaller. So we mark 5, and then we come from this side. Item from the right that is smaller than the pivot. So 6 is not smaller than 3. 7 is not, and 8 is not. 0 is. So you mark 5 and 0. We marked 5 and 0, and then we swap it.
Mm-hmm. Okay, understood.
Hmm. Then we repeat the same process. Okay.
Mm-hmm.
This time, so over here, if you noticed, item from the left remains on the left, and item from the right remains on the right. Okay, just remember this. And over here, when we try to do the same thing, compare it from left. So this is from left. It should be larger, L and L.
So I found
Left.
5 larger.
Yeah. So you found five larger, and from this side, we found zero smaller.
So swap it.
No, but over
Why?
here, what happens is, if you noticed in the previous slide, this left is before and right is later. It was
Hmm.
always the case. Left is before, right is later.
Hmm.
Over here, that is not the case.
So we leave it.
So this is when you stop searching, doing this step,
Okay.
item from left and item from right. So you stop doing that, and
Hmm.
instead you swap the item from left with the pivot.
Okay. You mean item from the right with the pivot?
No, I meant item from the left. This is item from the left, right?
Okay.
Swap item. Oops. Swap. Uh-huh. Swap item from left with the pivot.
Yeah. So now you got 3.
So now you got three over here and
What's
five
pivot
over
now?
here. So pivot was three. Okay.
Hmm.
And but now when once you have done this step, three is in the right position.
Hmm.
That's what we find out. Our pivot is in the right place. So everything left of it is smaller, everything right of it is bigger.
Hmm.
So 3 is in the right place now. Now this divides the array into two parts, the left and right. Now
Hmm.
we do the same thing with 210 and 8765. So now again from this we'll pick a pivot. We have to sort 8765, right? So we pick up pivot. Let's say we pick up 7. Okay, pivot is like randomly you can pick.
Hmm.
Okay, so it was 8765. So swap the pivot at the end. So seven goes to 5 and 5 goes to here. So it becomes 8567. 8567,
I'm
right?
stopped. I've stopped looking now. Let's move on to the next. It's just getting too much.
Okay, so in if you've understood till here, it's
Yeah,
basically
yeah,
after this.
I've understood that, but I've understood, but like I'm just feeling like there's too much of concept to remember in for tomorrow. So yeah, I think we should stop here for the sorting algorithms, and
Okay, so
yeah, it's
hmm,
getting too complex, especially this quick sort.
yeah, so I was just saying, after you've done this, you can simply write that repeat the process, and
Yeah, that's better.
by recursion, the let recursion handle the rest. So
Correct.
you continue that, and like this is comes in the right spot, and then you say three is in the right spot and seven is in the right spot, and then continue for these guys, this guy, and this guy. So you
Okay.
have this.
Sounds good.
Yes.
So now, so Kritika, you done with the all the explanation of the sorting?
There's this algorithm if you want to get
Let's
into.
skip that. Skip that. Skip
Okay.
that.
Okay, yeah, I think I'm done.
Okay, so I'm just going to go through the non-blue slides and
Right.
just go over that quickly. And whichever is easy, we'll pick up that. Which you don't understand, we'll move.
Yes. Oh, and I highly recommend you watch the videos that Sumaya shared for the
Have
sorting
you put them?
algorithm.
So put them on the slide itself. Maybe
I've
like
put,
create
put it.
another.
I've
You
put
did
it
that
there.
already, great. Okay, yeah.
Yes, for quick sort notes.
I don't know if
It,
I'll have the time tomorrow morning because I'm also working.
it's
But
literally 4 minutes and 3 minutes, and if you like watch even at that same speed, you'll get it enough to at
okay,
least write an exam. But even if you don't remember the exact thing, you'll write something.
exactly, that makes sense. Yep. Thanks for boosting the morale. Okay. Yeah, I think just the gist of these notations basically, because in case if it comes in exam, at least we have some idea about them. Rate at which required storage or consume time grows as the function of problem. Yeah, so complexity is like the rate at which required storage or consumed time grows. It should be simpler. Required storage or time consumed. Or just keep it this way. Required storage time grows. So basically, the rate complexity is the rate at which either the time or the space grows for a particular problem in size. It's a complexity. Bigger notation is a formal way of expressing the upper bound of an algorithm running time. It measures the worst case complexity or the longest amount of time an algorithm can possibly take to complete. We typically consult big O because you must always plan for the worst case. For example, O n log n describes the big O of binary search algorithm. So, just to give you like in one liner, big O notation is to deal with the upper limit. Like, what is the worst that can happen? If I write a particular set of statements, or if I run one loop, two loop, what's the worst that can happen? You know, uh, with time, is it going to grow? If it's going to scale or not going to scale? What's the worst that can happen? We're not going to look at the so that set of statement might have few elements to it. Some may be fixed part, some may be variable part. So let's say that we have an n square plus 1. So we can ignore the one part there because one is not that impactful. We have to look at the upper bound. What is going to cause the most impact? So n square is going to cause the most impact because it's growing like double the size. So bigger, whenever you talk about bigger notation, think about the upper bound, the worst case scenario. So that's what the bigger notation is. Omega notation is the formal way of express the lower bound. So just the reverse of that. Omega is the reverse of the big O. It measures the best case time complexity or the best amount of time an algorithm can possibly take to complete. Just the reverse. I don't know why I would look at the omega if it's okay. Bubble sort has a running time of omega n because the best case scenario, the list is already sorted. So yeah. So there you had binary search, O n log n. Here you have example of bubble sort, which is already in the sorted order. So omega n. Moving on. Theta notation is the formula for expressing both lower bound and upper bound. So I think it's very easy to remember these three, notations. Bigger notation talks about upper bound, worst case scenario, worst case complexity, longest amount of time or space. Omega is talks about the best scenario, which is the least amount of time any algorithm is going to take. Example, bubble sort. And theta notation talks about both upper as well as the lower bound. It's used to analyze the average case complexity of an algorithm. Clear? We already discussed this. We don't need to worry about two important attributes to analyze an algorithm is performance and complexity. So, in case of examination, they ask about analysis. We talk about performance and complexity, and then we break complexity into two. But if they talk only about complexity, then we break that into two, which is time and space. Moving on. Calculation of storage and runtime complexity. As memory is becoming more and more cheaper, prominence of runtime complexity is increasing. It is very important to analyze the amount of memory used by the program. If the running time of algorithm is not good, then it will take longer to execute. But if it takes more memory beyond the capacity of a machine, then the program will not execute at all. It is therefore more critical than the runtime complexity. I hope you understood that. Arrays pointer structures. Simplest form of array is one-dimensional array that may be defined as finite order set of elements. Moving on. C compilers, array of bounds, move on. Pointers and arrays are closely related. An array name without an index is a pointer to the first element in the array. We already know about pointers, so moving on. Sparse matrices. Matrices with good number of zero entries are called sparse matrices. Good number of zeros. Triangle Triangular matrices is a square matrix in which all of the elements either above or below the main diagonal are zero. The triangular matrices are sparse matrices. The tridiagonal matrices is a square matrix in which all the elements except for the main diagonals are the immediate upper and lower side of zeros. Okay. So may I have you read about this?
Yes.
Can you just explain in maybe few statements? Be precise.
Uh, Triangular matrix.
Sparse matrices.
Sparse matrices are just matrices that have a lot of zeros.
Like what? Show me in this diagram. What are you talking about?
So this is the first part. That's a matrix. That's a sparse matrix because yeah, uh, it has some zeros. A triangular matrix is one in which the non-zero elements they form a triangle. So, for example, if we had 1, 2, 3, 0,
Hmm.
1, 1, and 0, 0, 4, that would be triangular.
So same elements forming a triangle.
This is not triangular because we have a 0 there on that side.
No, I'm talking about this guy.
Oh, that is something else. That's a three tuple representation.
So we don't have an
Uh,
example of a triangle matrix.
no, there's no example. So sparse matrices, if they have a lot of zeros, then they take up a lot of unnecessary storage space. So there is a different way of representing them. That's called three tuple.
This one?
Yeah, this is triangular. And the other thing, tri-diagonal, is the diagonals are filled and the others are zeros.
Even the one that we have here in the example, this is also triangular because the main diagonal is 114 and below it's 000. So this is also
Oh,
triangular.
okay.
Yeah. Okay. Representing sparse matrix in three tuple form, first row always specified the number of rows, number of columns, number of non-zero elements. Each non-zero element is stored from the second row in the third column. Let's move on. Structures. What? Nobody put structures here. Polynomials, we don't know. Okay, so Maya, you're gonna do the honors. Structures have you studied?
No, I don't know what is the structures.
No problem.
What is it
Moving on.
referring to?
It's in the syllabus. If you that's what you're asking. Okay, hold on. Oh, okay. Got it. Got it. What we were studying are actually the structures, data structures. We are studying data structures and algorithm. We don't know what structures are. Shame on us.
Seriously, shame on us.
Seriously, yaar. Data structure is a way to store and organize data. What if they ask us what is data structure? I mean, it's silly. They'll ask, but what if they ask? You don't know that. It's a way to store and organize data so it can be used efficiently. Array pointer, structure, linked list, stack, queue, graph, searching, sorting, programs. So basically, whatever you've studied, just put everything there, shove everything there. It's data structure. Way to organize and store data. Polynomials. Oh, it's there. Nice. Oops. Like 5 into 4 plus 2 into 3 plus 7 into 2 plus 10 into x minus 8 can be represented using arrays. I still don't know what polynomials are.
Those are supposed to be exponents.
5
5x raised to 4.
Oh, okay.
2x cube.
It looks like 5 into 4. So, what are polynomials? We studied in the, I guess,
Maths.
yeah, I forgot what they are. Arithmetic operation like addition, multiplication of polynomials is common. Most often, you need to write a program to implement this operation. The simplest way to represent polynomial is, and is to store the coefficient. Yes, I remember this word is to haunt me in my childhood. Coefficient, polynomial. I used to hate it like anything. Terms of, and I don't know. At those times, the teachers used to teach us in a way that we sound so complex.
All my life, I've only studied what I've studied on my own. This teacher thing never happens. Like, even for this test, my brother said that DSA and DBMS, these are like very difficult topics. You should like try to find a tutor or something.
Hmm.
And I actually did find a tutor, but I
Hmm.
realized that if they teach me, I'm never gonna learn. I only learn when I study on my own. So
Excellent.
it just doesn't work. Group studies are a
Yeah.
lot better, and I told my brother that group
Hmm.
studies are better than the tuition teacher that you wanted me to have
Yeah, at least
because
you can have some fun while learning. And if you don't understand, just say it. I can't get it. Just leave. Just move
yeah,
on. Yeah, you
and
can
like
be a little less
you know
formal here.
yesterday I read somewhere it said that um the I don't know what it was exactly, but it was like if you want to learn, don't learn from the teacher, but learn from the best student. And you guys are
Hmm.
the best students.
We are not best student. At least Sumaya is. I'm not.
No,
Sumaya, I think studies at least 25 hours and 24 hours. I can bet you on that.
I took this week off to study.
Week off, you work, Sumaya? I didn't know that.
Yeah.
Okay, where do you work?
I teach online.
Oh my God. Really? On all of this time you've been hiding this information? My
No,
God.
I mentioned
Okay.
it before.
You did? Okay. Then my bad. I
Yeah, I
don't
think
remember.
the first time.
Okay. So, online means what? Like, where do you teach?
In an online school. So I
Oh,
teach
okay.
primary school kids. I teach
Oh, okay.
coding.
Coding you
Wow.
teach? Wow. Wow.
Yeah.
Amazing. That's really nice. You should try on your Udemy also. You should try creating some courses on Udemy because that's one way of earning also. It's like a record, you create once
Yeah.
and then stays forever. Of course, in programming, you still have to update your course after a few months, at least once in 6 months. But yeah, it's just a good way. Maybe start your own YouTube channel, something like that. It takes time to grow. If you start now, maybe in 2, 3 years' time, you never know. You might start getting something if you're interested. And Kritika,
Yeah,
by the
think
way,
about it.
your skills are also really good. I mean, I'm telling you honestly, I'm being a teacher myself. Your skills of teaching is really good.
Yeah.
Wow.
Not that,
Like I
not
remember
that,
all the things
yeah,
you taught.
yeah, not that you have to take this as a profession, but to tell you it's one of the skills that you excel. You see, there are so many skills in us which we wouldn't know until we explore them, like if we do something. So that is why you should do more things in life, because when you try more things in life is when you get to know if you're good at that thing or not.
Yes. Yes.
Correct.
Yeah.
Moving on. Tomorrow is not philosophy or class or so sorry, exam. So we have to move on. Sorry about breaking the interesting
Well,
conversation here.
thank you. Thank you. I really appreciate
Welcome.
that.
Welcome. Welcome. Okay. So arithmetic operation like addition, multiplication, polynomials. Let's move on. I don't think they'll ask polynomial. Representation of arrays. The elements of the array are stored in sequence to extent possible. If they are being stored in sequence, then how are they sequenced? Is the element is it that the elements are stored row wise or column wise? The former is called row major order and latter is called the column major order. Row major representation, the first method of representing a two-dimensional array in the memory is the row major representation. Under this representation, the first row of the array occupies the first set of the memory location reserved for the array, and the second row occupies the next set, and so forth. Column major. Second method representing a two-dimensional array is column major. Under this, first column of the array occupies the first set of the memory location reserved for the array, and the second occupies the next set, and so forth. Okay. Lists. Arrays are data structure of fixed size. Insertion, deletion involves reshuffling of the array elements. Thus, array manipulation is time consuming and inefficient. In this unit, we'll see abstract data type lists, array implementation of list and linked list implementation, doubly and circular linked lists, and their applications. In linked list, items are added or removed easily to the end or the beginning. So I think what the point they're trying to make over here is that compared to arrays, lists are better for insertion and deletion, because generally arrays are of fixed size unless you're using dynamic array with heap memory and stuff. Arrays are of fixed size, so list helped you in this performing this manipulation. Abstract data type list, ADT. In the exam, if they ask you ADT, don't get scared. It's just talking about list only there, and just full form of abstract data type. So there are many abstract data types, one of which is list, and I think you have linked list also. A list of elements of type T is finite sequence of elements of type T together with the operation create CRUD for empty testing, for full finding the size, traversing the elements. ADT is useful for specifying the logic properties of the data type, and ADT is a collection of values and set of operations on those values. Okay. Mathematically speaking, a type is a set, and elements of set are values of that type. Okay. Array implementation of list will use array to hold the entries and separate counters to keep track of the number of positions are occupied. A structure will be declared which consists of arrays and counters. Insertion, deletion. Okay. Linked list is a chain of structures in which each structure consists of a data and pointer. We already know linked list. I don't think we need to even read this. Move on, we'll save time. Algorithm, insertion of elements into the list, deletion. We already discussed about this syncly. You already know this. We know doubly. That's great. This is how that looks like, by the way. If you have not seen the diagram, this is how it looks like. You see that? Previous, next, head. Previous is null. Here the next is null. So if you get to draw a diagram, you know how that looks like now. And this you already know. Implementation, circly linked list implementation. Yeah, we didn't do circly linked list, did we? We didn't. So Maya, do you know what
No.
they are?
So the last element of the list, instead of pointing to null, it points to the head, to the starting element.
Okay. Okay. So we did singly, we did doubly, we didn't do circularly. What is that called? Circle linked list. Yes, sir. Nice. Where is the circular? Hey, didn't do this cheating. Is a variation. Oh, okay. Variation of the linked list in which the first element points to the last element and last element points to the first element. Why they are not showing the diagram? Is this the diagram?
No, this is single. Oh, I don't know.
But it's saying as
No.
circular here. So first element points to the last, and last element points to the first. So both singly and doubly can be made into circular linked list. How? Next is first.
Hmm.
In
Next is
singly,
first.
the
First and
last one will point to the
understood.
first.
Understood. And then in the singly, yeah, in the singly, last one will point to the first, and that's it. End of story. And in the doubly, last will point to the first, and first will point to the last. Yep, understood. Not bad. I think we can write it in the exam very easily. Nice. That's the power of group study. This is all we are supposed to write, but it's okay. I mean, we don't have time for that, anyways. I think we should create another slide here and put that there for future reference. Who's going to copy? Just, I'm glad the screenshot existed. And I imagine if they didn't exist, you have to write everything. Cool. Moving on. How many slides are there? Oh my god. Don't tell me. No. Stop. Think we will do as much as we can. Which slide are we on?
48.
Okay. Stacks. We can skip some of the slides now because we already know what stacks are. So moving on. Not gonna worry about it. Still, I'll read just a little bit. I'm greedy. What was the greedy algorithm? Which was the greedy algorithm? Which
Prim's algorithm.
Prince algorithm? I don't even remember what Prince algorithm is now. Okay, fixed size initially involves reshuffling. Same thing, I think. I think I just copy pasted without understanding that it's not really. Yeah, it's not part of this. Yeah. Again, we know what stack is. We can just skip this slide. If you want to just have a look at it, you can look at it. So top int array stack top equals -1 push pop is empty display. This is how you create it. This is how you push it. Okay. Implementation of stack using, you never know, yeah. These guys can ask, can you give example of implementation of stack using linked list? Can't say much. In data node next. I will node top push pop display. Okay. I think we can build concept in this little time that we have. You've done all of this, Sumaya? Implementation on stuff?
Yes, I did. I did part of it.
Okay, no problem. Algorithm implementation of multiple stacks. So far we have been concerned only with the implementation of single stack. What happens when the data representation is needed for several stacks? Let's see an array X dimension M for convenience. We shall assume array comments from 1 and ends at m. If we only have two stacks to implement the same array x, then solution is simple. Again, this requires building of concept. Do you remember anything on this front? Multiple stack implementation? If you can explain in few sentences.
No, I didn't
Okay,
understand
leave
this
it
so
then.
well.
Just leave it this. Queues. Yeah, so what do we have? Circular queue and the normal queue, linear queue. And we already have enough information about that, so we're going to just move on. This is a program implementation. I guess whenever they talk about implementation, they're talking about the program. Just take a look at it. Structure, struct queue, int elements, queue length, front, rear. So this function is add struct queue, int value, rear, queue length. Okay, I don't think I'm going to remember that, so it's fine. Okay, moving on. Okay, moving on. Multiple queues, nothing there. Priority queues. Graphs. We did some of the graphs, right? Shortest path algorithms. Dijkstra's algorithm. Graphs with negative edges, acyclic, all pairs. Single source shortest path algorithm. Here, single source means that only one source is given, and we have to find the shortest path from that source to all the nodes. I'm just moving on because we don't really have time to even take a look at these guys. Minimum cost spanning trees. Spanning tree is a subset of unidirected graphs that has all the vertices connected by the minimum number of edges. Yeah, in case if they ask us like what is spanning tree, I think we should at least know that. Maybe in short notes if they ask us. So a spanning tree is a subset of the unidirected graph and has all the vertices connected by the minimum number of edges, and I guess without completing a cycle. Minimum spanning tree is a subset of edges of connected weighted and unidirected graph that connects all the vertices together with the minimum possible total edge weight. To derive an MST, Prims, is it Prims or Prism or what is it? Prims algorithm or Kruskal's algorithm can be used. So yeah, in case if they ask us about spanning trees, we can tell them that it's a subset of the unidirected graph with the minimum number of edges where all the vertices are connected without forming a circle. And to derive a minimum spanning tree, there are two algorithms which are used. One, Kruskal's, we already know about, and then there is another one, Prims. Okay. Kruskal's we already read about. Wait, did we not? Did you not move this? We did, right?
I
You
moved
copied
it,
it, I
I
guess.
duplicated it.
Oh, that's good. That's good. Then fine. Prim's greedy algorithm. Yes, that's the greedy algorithm. At least I know one thing about this algorithm. It's greedy. Oh, they might ask us the difference also. You never know. Hey, where is the example of Prim's algorithm?
There
I
is a
think he
link
explained
to
it
it.
through the link, right? He didn't really
Yeah.
put that there. Okay. I'm just going to try to recall what happened there. So we chose the vertex. So Maya, do you remember this? How this algorithm was? Can you remind us if you remember?
Yes, I remember.
So say,
Can you scroll up?
yeah.
Okay, so this is the graph. First, we choose a vertex. You can choose any vertex, I think. So they've chosen B.
Which was B. Yeah, okay.
Yeah. Now we have to choose and add the shortest edge from B. So the edges from B are 4 and 10. We add the shortest one.
Yeah.
Now
Okay.
we have the edge BD. Now we
Mm-hmm.
have to see if they are connecting to any unvisited vertices. And you have to
Yeah.
find the smallest one.
Like E and C. So
Yes.
smallest is 1.
Yeah.
We
So
put
we
that
add
there.
that.
Okay. Then next.
And then now from BD and E, we check the smallest vertex, which
Which
is
is 2, 10, and 6.
2.
So 2 wins. Put that
Yeah.
there.
And then there's only that one remaining. So we add
Yep.
that.
Nice. So I think we should add it. Like with that guy there, because then it'll be easy for us to just recall this. Or maybe just leave it there. It's fine. I think we can click on the link and go there. It's fine. Considering we only had 74th slide yet, we have to move on. Breadth first search. Depth first search we did. Want to know what breadth first search is? When vertices of the graph are divided into two categories, which are part of the visited as part of the search, and those vertices which are not visited. 1 second.
So breadth first search is very similar to depth first. Only instead of using a stack, we use a queue.
Okay. Is it the part of that breadth first search?
No.
The second, right? No. Is there a link?
Uh, no, I didn't put a link.
Okay. Breadth first search. Not good. That example was good. That site was good. You know, the one I put the example.
Yeah, they also have it.
Where?
I think it was there in the results.
But where?
The last one, BFS graph algorithm.
This
The
one?
program is, yeah.
Yeah, this is what I was looking for. Great. So let's see. Q. 1, 2, 3. All they're doing is just replacing the queue, nothing else. I don't see there's any change here, apart from the fact that
So
they've replaced.
here, uh, can you go up?
Yeah,
Yeah, right. Uh, right at the second last step, there's a difference there.
I'm gonna go from
Okay,
the top. So
okay, okay.
0, 1, 2, 3. Good. Move the one over here, and so on. Move two here, so on. Then three here, and that. What's the
So here
difference?
it's a queue, so they're adding the elements at the back. So the difference here is in the depth first search we went 0, 1, 2, and then 4. Here we're going to go 0, 1, 2, and then 3. So the new things that
I'll open side by side. Probably that'll help me.
okay.
Depth. What program is? So they had one, two, three. One moved up, the remaining two, three. Then two moved up, three and four. What's the difference? Why is it four and three here?
In the stack, when they're adding to the front, and in the queue, they're adding to the back.
Oh, okay. Okay, I get it. I get it. So here they added one, two, three from the top. Then is already there, so it didn't do anything. Then a new number was four. So Q they put four at the end, but here they put four at the beginning in the stack, right? That's the difference.
Yeah, yeah.
Understood. Understood. Cool. That's easy then. I'm very like I'm happy that see that's the advantage of covering the ones that are not marked as blue because some of these are very similar. Even if we spend 2 minutes, we can grasp the concept and write it in the exam. So I have a new concept just in 2 minutes. But if you don't look at them at all, when it comes in exam, we're kind of losing it, right? So now we have two superpowers: depth first search, and breadth first search. So if any of them, I'm pretty sure if they talk about they will only give from these two, either this or that, if they want to give it. And whichever they give, we'll be able to crack it. So that's good. Finding strongly connected components. Strongly connected components is a portion of a directed graph in which there is a path from each vertex to another vertex. It is applicable only in the directed graph. What's that?
There was an algorithm for this for finding strongly connected components, but it was very confusing.
Okay, let's move on then. Trees, we already know what trees are. Moving on. Tree traversal, pre-order, we already know. Great. Already know binary trees. Great. Advanced trees, binary search, we know that. Already know that. Three types of traversals. Excellent. It's a repetition. Great. Did you make this so ugly? They didn't even draw the circle properly. I don't think they did the insertion of a node in a binary search tree. So let's take a look at that. Allocate the memory for the tree, set the data to the value, and set the left and right pointer tree. Point to the null in the item will be first element of the tree, then right will be point to the null. This will take time. Deletion, yeah. I think probably tomorrow, when you have time for yourself, you should study insertion deletion of the binary search tree because might be important. I'll color these slides. Anything to do with the binary search, I think it might be important. I'm just getting a feeling. What color do you like, Kritika? Pink is fine.
No, not pink, green.
Ah,
Why would you put pink? I don't like. Nobody likes pink.
I just put it because I found it easier. I mean, I don't like any of these colors from here, if you ask me. I like sober colors, like how these foreigners wear sober colors. I like those colors. I mean, I would never wear like this hard. These are hard colors. Like there's no subtle feeling in these colors. These are like if you go to a local Chindi market, you get hard colors compared to if you order something from Mintra.
Appavalvan chalk.
Yeah, yeah. I've been a long time been there. ABC, you couldn't have said ABC. You really had to bring that feeling out of Appa Balwanda. Yeah, if you were in US, then you'll say ABC chalk, but here you will say Appa Balwanda chalk. Very smart. Mm. Okay, AVL tree is a balanced binary search tree which has following properties. What the heck is AVL? AVL tree is a balanced binary search tree. Okay, it says balanced tree. So tree bit difference, I guess, is a balanced. Main word is balanced. Subtree of every node differs in the height by at most one. Subtree of the very node differs in the height by at most one. Every subtree is an AVL tree. Insertion of a node. Nodes are inserted into AVL tree in the same manner as ordinary binary search tree. However, the insertion of the algorithm for an AVL tree travels back along the path it took to the first point of the insertion, checks the balance. That is unbalanced if it has a balance factor of either -2 +2. Rotation is performed. Balance AVL rotation. It looks interesting. Left rotation. In left rotation, every node moves in one position from left uh, to left from the current position. So left rotation. Okay. Okay. Balanced. So right is unbalanced tree. Then left rotation to make it balanced. Then right rotation. So left is unbalanced. To make it balanced, you rotate it towards the right, so becomes a balanced tree. So right rotations are combination of a single left rotation followed by a single right rotation. Right left rotation are combination of a single right rotation followed by a single left rotation. So who's written this maybe can explain.
I put it.
Okay, tell me. So, what are these AVL trees, first of all? So, my understanding is that they are balanced. So, when you say balance, what do you mean by balance actually? The number of children?
No, the height of the subtrees. So
Okay.
the height is like here in this unbalanced tree, it is 3. And if
Yeah.
you look at the subtrees of A, then the right subtree has a height of 2 and the other side has a height of 0. So it's unbalanced. We should have a
Sorry.
difference of at most 1.
Say it again.
So in this unbalanced tree, the right subtree has a height of 2 and the left one has a height of 0.
Okay? Which picture are you referring to? The left rotation or the right rotation?
The left rotation,
Okay. So
right
you're talking about the
unbalanced
right
tree.
unbalanced tree where I can see
Yes.
A has 2 and C has 0. Okay. Go on.
So it's unbalanced because the difference of the height of its subtrees is more than 1.
And what are subtrees in this? From A, B, and C, what part of it is subtree?
A BC
B and C.
is the right subtree
Subtree.
of A, and
Okay.
there's no left subtree. The height
Okay.
is
So
0 over there.
height difference is more because the height difference between B and C. Sorry, B and C is 1, and A and B is, you mean, 2. What was the
Uh,
height
y-
difference you're talking about?
yes, there are two nodes B and C, so the height is 2.
Hmm. Okay.
So we just count like the levels of the tree to find the height.
Okay.
And the difference between the heights of the left subtree and the right subtree should be at most 1. It shouldn't be more than 1. So if it is more than 1, then we have to perform one of these rotations. So in this right unbalanced tree, they've done a left rotation. Um, B is moved to the left up, and A becomes a child of B, and now it's balanced.
Okay. I'm still not getting the height part. Can you explain the height part? How is the height calculated?
Uh, I think if there was a better example, it would be easy to explain.
Yeah. I read about it, but I don't remember the calculating the height.
I'll try to find a better diagram.
Okay, no problem. Don't worry about that right now. Let's move on. At least we've got
Okay.
some information that we can use in the examination. So basically, avial trees are more all about balance. The sub trees need to be balanced. If they are not balanced, then we rotate them either in left or right direction, depending on what's suits the best, and then we balance it. B trees. B tree, Kritika must have remembered. Do you remember what B tree is, Kritika? It's a multi-way search tree. All leaves are on bottom level. All internal rows have at least m by 2 children. The root can have as few as 2 children if it is internal node and can have no children if the node is a leaf node. Okay. Each leaf node must contain at least m by 2, one key. Operation, search, create, insert. So, what's the summary of this B trees?
Uh,
Sorry?
Sunaya, go ahead, please. I don't know.
uh, so it's like a binary search tree, but uh, it can have an order of more than 2.
Hmm.
So each node contains keys. There should have been a diagram here. It's difficult to explain otherwise. So each
Yeah.
node contains keys, and um, they have child nodes that point to keys that are lesser or greater.
Okay. Okay. Splay trees. Okay, what are splay trees? Splay trees are self-adjusting binary search tree in which every axis of insertion or retrieval of the node lifts that node all the way up to become the root, pushing all other nodes out of the way to make room for this new root of the modified tree, like a boss. So let's see how that is happening. So Somaya, you might be able to explain this, what's happening here. How is it pushing it to get make its way up to the top? And why would it do that?
I didn't really understand this so well.
No problem. So I think just some summary of what splay trees are. They are self-adjusting binary trees uh, in which anytime you insert a new node into it, or retrieve or remove a new node, remove an existing node, it's going to lift that node all the way up to become a root node, pushing all the elements out of the way. Okay, so if you insert a new guy here, it's going to make his way up and become the root node. Moving on. So there's more here. Hence, frequently access nodes will be frequently be lifted up and remaining around the root position, while the most infrequently accessed nodes will move farther and farther away from the root. Splaying is a process in which node is transferred to the root by performing suitable rotations. There could also be rotations also. So splay tree main thing is that the the node is going to make its way up to the root, especially when you insert it or if it's frequently used and stuff. Okay, go on. Red black trees. It's a special type of binary search tree with one extra bit of storage per node. Its color, which can be either red or black. So, Kritika, if you don't remember anything about all of these trees that we are talking about, if it comes in exam, one statement you can write is that this is the type of binary search tree. For splay, you can write node makes its way up, pushing all of the others to make room for themselves, to make room for itself. And for red black, you can see you can talk about the node has this color, either red or black. You can derive that from that name itself. Yeah, I'm just giving you some context in the exam.
Yeah.
So because they are binary search trees, and if you don't understand anything, just write more about whatever you understand about binary search trees. At least you'll fill some content, because these are type of binary search trees. They are the binary search type of them. Moving on. Properties. Each node should be either red or black. Okay. The root node is always black. If a node is red, then children should be black. Root is black. If a node is red, children should be black. Okay. For every node, all paths from a node to its leaves contain same number of black nodes. Okay, we got it. Red black trees insertion. You see, root is black, and anytime a child is red, then the pair. Sorry. Anytime a node is red, then the child should be black. I don't see that in this case. That's the case.
This is showing a red black tree violation.
Okay. Okay. See, this is following that. So root is black, great. If any node is red, child should be black, which is this. I guess this is not following that. Uncle, grandparent, whole family is here. AA trees. How many trees are there? Yeah, come on, give up on us. AA trees. I only remember AA batteries here.
This,
AA trees are
all
there.
these trees were so difficult.
Yeah. What do you think? Algorithms are very easy. What? They are also difficult. The whole subject is difficult. I really pray to God that tomorrow, whatever we've studied in the blue sky, only that comes and we're able to write it. I'm going to remember red and black from this. I can at least write in the exam that nodes are either red or black. Okay. From this play, I remember that basically when you insert a node, it'll try to make its way up to reach the root node. So at least I remember that part. Um, then AA trees are defined in terms of level of each node. This information of level of node is stored in smaller integers, maybe 8 bits. The level of node will be as follows. Same of its parent if the node is red. One of the node is leaf. Level is too much. Move on. Linear search. Nothing is there. Internal sorting. We do this. Oh, internal sorting is has these types that we discuss: heap sort, two-way merge sort, quick sort, bubble sort, insert sort. So if they tell us in the exam, so this is what I'm talking. The reason why we are studying this is because at least we know where these under what topic these falls. Like for example, in exam, if they ask you, give list down a few internal sorts and explain them. Now, although we know bubble sort, although we know quick sort, we won't be able to write because we don't know where they belong. So So by reading this, at least we know that these guys, all these sorting ones that we've studied, they belong to internal sorting. We at least, I remember in one of the exams they ask about what type of conditional statement. No, no, what statement where we had break and stuff. In one of the C program, they had conditional statements, control statements, right? Control statements, yeah. So I didn't know what control statements. I just guessed it like it would be break or continue. But if I would have studied, at least I would remember. So that's the thing. Anyways, internal sorting is insertion, bubble, quick, two-way merge, and heap.
Two-way
Merge
merge
sort
sort and
is
Sorry, sorry,
I
merge
was
sort is external. What do you say?
really?
yeah,
Okay, yeah, it's not here.
yeah. I was asking if merge sort and two-way merge sort is the same thing.
Hmm, not sure.
Yes, I think two-way is a type of merge sort. You're dividing into two halves, and maybe the other types in which you can divide the array into more halves. More.
Okay.
Where is the list? It's coming under internal sorts, Maya.
Uh,
See that?
I don't know why they listed it there.
Yeah, I picked up all these topics from this guy only. Anyways,
Okay.
coming back. So internal, I know, I remember. I'll be able to write about insertion sort for sure, because it's just like when you're given like cards and you can arrange it. Bubble sort I can write. Can write quick sort. Quick sort I don't remember easily.
I taught quick sort.
Dot quick sort. What was it? I forgot.
Item from the left, item from the right, put the pivot at the end.
The difficult one, right? Which
Yes.
you're talking. Yeah. See,
Yes.
that's why I don't remember. Anyways, heap sort. Okay, so two-way merge sort. I'm not gonna go with it. It's fine. Moving on. It's already explained. So I already explained that. Heap also. Heap sort example. Fine. Insertion sort. This was the easiest.
Hmm.
Quick sort. Because it had pivot. That's why I don't remember. It's too much of going on. Okay. I'll still take a look at it in the morning if I have time because I'm working tomorrow. Level order.
Oh,
Sorry.
damn, how are you gonna work tomorrow and then give the exam? You're taking half day?
How am I gonna do that?
Tomorrow is a Friday. Okay.
The problem is that um, one second.